Welcome to Lecture 12. We are going to talk about precipitation reactions today, which are an example of double replacement reactions or double displacement. Remember what I said in the last lecture, replacement, displacement are used, different books use different terms. You'll hear me using both terms. Just for your information, single replacement reactions or single displacement reactions sometimes are just called displacement or replacement. The single is not always used. But this is the type we're going to start with. At the end of Lecture 11, I talked about the classification system for reactions that you probably learned in high school. Then I also talked about the fact that there are really two types in your book in Chapter 7. Starts off with that classification system, and double replacement reactions are the class of reactions where there are no changes in charges or oxidation numbers. So this is going to be helpful, and it's a good place to start. The term oxidation numbers, we will discuss that later, as well as the class of reactions called redox. But this type that we're going to start with today, and also the next lecture, is this first type, no changes in charges or oxidation numbers. And what I've put here is one of the figures from Lecture 11, and I talked about it in that lecture, in that we are taking a dissolved ionic compound, usually, and so it looks like you're adding water. So it's a homogeneous mixture, a solution, and you're adding it to another dissolved ionic compound. And you're adding it to another dissolved ionic compound, which is also in solution, which means that it's very homogeneous, looks like water. So dissolved ionic compound. When those two ionic compounds interact, there are four ions in all. And I'm going to show you, first of all, what this means so that you'll have a better understanding. And then we're going to take those four ions and we're going to discuss what can happen in order to form what we call a precipitate, which is simply a solid. And that's the types of reactions we're going to talk about today. So double replacement reactions that result in a precipitate. We'll talk. There are other double replacement reactions, such as those involving acids and bases, and we'll talk about those in the next lecture. So let me go ahead and scroll, and I'm going to get down to a little simulation, a little video that shows you what dissolving really means. Waiting for it to come up.
Let's add a small amount of table salt, sodium chloride, to water. As you know, sodium chloride dissolves in water. Click on the zoom button to view sodium chloride. Polar water molecules interact with the positive and negative ions of a salt. The positive ends of the water molecules are attracted to the negative chloride ions. The negative ends of the water molecules are attracted to the positive sodium ions. This interaction between water and the salt ions causes a salt to break apart or dissolve in water.
Okay, a couple things I'd like to point out here, and that is that you are familiar with calling this compound salt, but in fact chemists call all ionic compounds salts. Here is our familiar water molecule, and now you know what polarity means. The oxygen atom here in the middle has the higher electronegativity in the bond that it's sharing with hydrogen. So that makes this end of the molecule slightly negative and this end of the molecule slightly positive. These ionic compounds will break apart for there are two things going on. There's more than two, but two main things energy-wise. It takes energy to break apart sodium and chlorine into its ions. So I can write a little equation. This is what we're doing. And you need to become familiar with this because this is what we're going to be doing when we write net ionic equations. So when I say, and the aqueous stands for water, and we could put water in here, but it would appear on both sides of the equation and would essentially cancel out. Another way of thinking about it is if this is written down as one of my solutions, that in that picture that we just looked at with the yellow precipitate, this is how sodium chloride would be written. When in fact, from what I've shown you here, that it is not sodium attached to chlorine, it is a sodium ion surrounded by water molecules, and that's what we mean when we write AQ afterwards, and chlorine surrounded by water molecules. So if I have two, I'm going to go back to the notes. If I have two of those ionic compounds in my picture, then can you now see why I have 4 ions altogether? So this first one may very well be, I'm pretty sure I know what this is, but it really doesn't matter. Let's just talk about it in terms of the general equation for double replacement or double displacement reactions. So this dissolved ionic compound is AB aqueous, and we are reacting it with this dissolved ionic compound, which we are going to call CD aqueous. Okay? So they're both dissolved in water. What happens in a double replacement is the positive from one, double date switch dates, the positive from one goes with the negative from the other. That's one possible interaction that may cause a precipitate to form. Now we're going to talk about why the precipitate forms in a moment. So AD and CB, because I would write the positive first, so this is the other combination, are my two possible products. In most precipitation reactions, not entirely all, but in most, one of these is aqueous and the other one is my precipitate. Okay? And obviously from looking at this picture, one of the combinations is coming together and forming a solid. I always tell students that it's like those couples you wish would get a room. They are highly attracted to one another, and it's not very soluble, and that is why it forms the solid. So we're going to scroll down and look at the solubility rules, because the solubility rules tell us what dissolves and what doesn't. So again, what you have when you pour these two solutions together are some A+ ions surrounded by water. You have some B- surrounded by water. And you have some C pluses surrounded by water and some D minuses surrounded by water. You know, the B and the D aren't going to get together because they're negative. The A and the C aren't going to get together. They're going to avoid one another because they're both positive. So your possible new combinations are C with B and A with D. So that's what we have shown here in writing our equation. A is now with the other date's partner, and C is with B. The two together, either one is aqueous, the other is precipitate. I know that a reaction is happening here because I am seeing it. When I don't have that capability, I'm going to rely on the solubility rules to tell me whether or not a reaction is happening. All right, so what I'm going to do is go ahead and scroll down to the solubility rules. There are many different forms. Your book has these on page 216, right here, page 216. I really like the diagram in your book. In fact, that is the one that you will have on tests and so on. So how do I know when I have 4 ions in solution and then there are 2 possible new combinations, which of those combinations is going to, or might form a precipitate. You may put two solutions together and form nothing because none of the combinations lead to a solid. Therefore, you just have the same 4 ions floating around in solution that you had before. All right, so let's look at these solubility rules. It's kind of a top-down hierarchy, so the ones, rule number 1, rules out those below it. So anything essentially group 1A would be your sodium, potassium, and so on, and then ammonium. So pretty much anything with a sodium in front or a potassium or an ammonium. Of course, there are other ions in group 1. They're not very common, like cesium and rubidium and so on. Anything with a nitrate after it is generally soluble. So, lead nitrate would be soluble, even though most lead compounds are not. And then acetates tend to be soluble. Acetate is one of those polyatomic ions you need to know. Obviously, there's lots of polyatomic ion conversation here, and those are with us for the rest of the term. So acetate, again, is C2H3O2 with a -1 charge, or another way of writing it, this is the structural formula, is like this. So if this is behind aluminum acetate would be soluble. All right, all binary compounds of group 7A elements other than fluorine with metals are soluble except those of silver, mercury, and lead. So this means that pretty much anything you put in combination with chlorine, bromine, and iodine, because fluorine is an exception, except for these 3 is going to be soluble. So almost every chloride is soluble except for silver chloride, mercury chloride, and lead. These 3 elements in particular just tend to form very insoluble compounds. Anything in combination with bromine or bromides, except for these 3, are soluble. Same thing for iodine. Okay? Sulfates are soluble except those of barium, strontium, lead, silver, and mercury. So there's your lead, silver, and mercury. So this is your group 2s. And the reason for this one here is that barium sulfate is a +2 -2. Many +2 -2 compounds are not soluble because of the energy it takes to break them apart. That's one thing I did not follow up on when I was talking about the dissolving process, so I'll talk about it now. There are 2 things that indicate whether or not you are going to dissolve. One, the first thing that happens in order for dissolving to occur is you have to break apart the positive and negative ion. That takes energy. So the first thing that happens is you break the ionic bond to dissolve. The second thing that happens is you form, the aqueous ion, which means that you have, there's more things going on, but these are the 2 biggies. Form the aqueous ion, which means that you are surrounding that ion with water molecules. This takes energy. This here, the second one, releases energy. If the releasing of energy is not bigger than this, takes energy to break it apart, if this isn't larger, then the compound will not dissolve. And that's the reason these +2 -2s don't dissolve, is because it takes too much energy to break them apart. Okay? And then except for those in rule 1, pretty much all of your carbonates, your hydroxides, oxides, and phosphates are not soluble. So if it has a sodium in front of it, it is, or a potassium or ammonium. Most carbonates are not soluble, nor are the hydroxides or oxides. Now, yes, so this is a good little short list. The figure in your book on page 216 is more detailed, and I like it, but this is the one that I chose to put in the notes because it takes up less room. All right, so what we're going to do is do some practice applying the solubility rules first. And then we're going to do some combinations and put this into practice where we look at the double replacement reaction and the possible products that can occur. So let me just go, before we do that practice, let me just scroll back up. I'm going to lose what I've just written here. Let me scroll back up and remind you of the example that we started with. Okay, well, of course I've lost the ink here, but remember that we said AB plus CD goes to possible new products are AD and CB. Okay, those are our two possible new products. One of these, obviously, is not soluble. So you would check the solubility rules to see which one was your solid. The other one will stay aqueous, and you certainly can check that on the solubility rules as well. So that's how you would do it. You would take the formulas of your reactants. You can then pretty easily form the formulas for the products, go back to charges to form the formulas for your products. Do not carry subscripts over. You'll see when we do some examples what I'm talking about. And then you check the solubility rules to see which one of these is your solid. If they both dissolve, then you have no reaction. Okay, one more time. If both of your new products dissolve, you have no reaction. That is not the case here. Obviously, something is causing, some new combination is causing that precipitate because it forms a solid, not easily dissolved. All right, so let's apply our solubility rules with this first example. In fact, I think this is one of your recitation problems. Are these compounds in the correct column? And move any, to misplace to the correct column. So let's see. I think what I'm going to do is I'm going to get some more room here. Okay. So we can add to the column if we need to. If you have your book, go ahead and turn it to page 216, and that way I don't have to go back and forth up here to the solubility rules. I pretty much know them, most of them by heart. And let me just say one more thing before we get started. Soluble, insoluble. This means dissolves, okay? This means it does not dissolve. I know that I'm throwing around two different terms, dissolving and soluble. Solubility, we could talk about solubility at this point and actually quantify it and so on. It's temperature dependent, but we're not going to do that today. All right, so is lithium hydroxide soluble? Yes, it is. Lithium is a group 1 ion, so it trumps the hydroxide rule at the bottom of the solubility rules. So lithium is soluble and is in the right place. Calcium chloride, is it in the right place? No, it isn't. Most chlorides are soluble. Calcium is not one of the exceptions. So we're going to take that one out of that column. Sodium carbonate. Sodium is a group 1 ion. So that's your rule 1. So this one is soluble. Copper hydroxide. Most hydroxides are soluble unless it's those covered by rule 1. So this is in the right place. Silver chloride. This is an exception for the chlorides, so silver chloride should be in this column. Calcium acetate. Rule 2 says, and in the notes, that acetates are soluble, so we're going to move that one to the soluble column. Calcium acetate. I need 2 of those -1 acetates to cancel out the +2 on the calcium. All right, potassium phosphate is in the correct column because potassium is a group 1 ion. Strontium sulfate. Strontium is one of the exceptions. Most sulfates are soluble, but not strontium sulfate, so it is in the correct place. Copper iodide. This is a group 7 in a binary compound, and copper is not one of the exceptions, so this is in the correct place. Mercury bromide. Same rule that applied to this one, but mercury is one of the exceptions, so it is in the correct place. Lead nitrate. Rule 2, nitrates are soluble, even those with lead, so this is in the correct place. Lead bromide. Mercury, lead, and silver are our common exceptions to solubility, so this is in the right place. Cobalt carbonate. Most carbonates are not soluble unless it's those covered by Rule 1, which includes the group 1 and ammonium, so the cobalt carbonate cobalt Roman numeral 2 carbonate, belongs over here in the insoluble. And then lead iodide, another exception to the group 7's lead, so this one is in the correct place. All right, so this is what we're going to do when we write our products and we check to see which one is soluble and which one is insoluble. The insoluble is your precipitate. So when you get these combinations that do not dissolve, these are your precipitates. And that's a shorthand way of writing precipitate. All right, number 2, you are going to write this is your reactants, so you're going to predict your products. I think it's easier for students if you do it while it's a word equation. So potassium is going to go with acetate, and lead, no change in charge, so it will still be lead 2. Lead will go with chlorine. So why don't you pause the video and try this, writing the formulas of both the reactants and the products, and then consult your solubility rules to see which one of those products is a precipitate. I will tell you that you do have a precipitate here. All right, coming back, our product here is potassium acetate, most acetates are soluble, certainly something with group 1 in front would be, so this is aqueous, plus lead 2 chloride. And that is our precipitate here, because lead is an exception for the group 7. So that is my solid, that's my precipitate. So now I'm going to do the hardest thing that we're in now that we're in chemistry land, and that is writing those formulas, because you're still learning the language. You know, when you take a crash course in a language and then go to another country, you are not very good at it. And exam 2 material was a crash course in chemistry language, and now we're going to be applying it. So I do expect that you're going to have difficulty, but practice is what it takes to master any language. So that's what we'll be doing all during exam 3 material. All right, potassium and chlorine, thinking of charges. So now that we're in chemistry land, you will have both ionic and covalent compounds. If you have a metal, you know you need to think charges. If you see prefixes, which you won't see in the material we're doing today, then you know not to think as charges. Okay, this is aqueous, plus lead, that 2 Roman numeral means that lead is a plus 2. Acetate has a negative 1 charge, so I need 2 of those negative 1s to cancel out the plus 2 lead. Potassium acetate, I have a plus 1 minus 1, so here's my formula, and this is aqueous, plus Pb with a plus 2, and then chlorine with a minus 1, so there's my formula. Okay. Balance, let's balance it. That was something we learned at the end of in the last lecture. So we are going to take, there's 2 chlorines here, I only have 1 here, so I'm going to put a 2 there. That gives me 2 potassiums, and I need 2 acetates anyway, so I'm going to put a 2 in front. So now we're balanced. Of course, go ahead and pause and try B. I'm going to scroll so that I have that more in the middle of the screen, so we will lose what we've just done. I'm giving you a moment to pause if you can, to write anything down that you've missed. All right. Writing our products. Lithium chloride. And lithium is a group 1, so pretty much anything it's with will be soluble. So lithium chloride is aqueous. And strontium sulfate is an exception with the sulfates, so that is our solid. Strontium sulfate, solid. And now we're going to translate those into formulas. Your reactants are almost always, you can double check with your solubility rules, but generally those are dissolved in water, so they are soluble, are aqueous. So I'm going to start over here to make sure I have enough room. Lithium has a +1 charge, sulfate has a -2 charge, so I need 2 of those lithiums, and that's aqueous, plus strontium chloride. Strontium is +2, chlorine is -1, so I need 2 of those -1s, aqueous. To make lithium chloride, back to charges, do not bring that little 2 over. We will take care of the fact that it's not balanced when we balance the equation. This is +1, this is -1, this is aqueous. And then strontium sulfate, strontium is +2, sulfate is -2, so that is my solid. Now I will balance 2 chlorines, 2 lithiums, so if I put a 2 here, we should be good. Okay. Now the directions for this problem said if nothing, if everything dissolves, then write no reaction. We have not encountered one like that. So products for this next one are going to be potassium sulfide, which will be soluble because that's a group 1, potassium's group 1. And I don't think the solubility rules that are here in the notes mention sulfides. Most of them are not soluble, but certainly the group 1s would be. Plus calcium bromide. And I'm going to double check the solubility rules, but I don't believe that calcium is an exception. So I do believe for C that we have no reaction. I'm going to pause and go grab my solubility rules just to double check that. And I was right, calcium bromide is aqueous, so indeed we have no reaction here. So when both of your products are aqueous, you should write no reaction because you have no reactions happened. You've made nothing that is new. You still have the same 4 ions floating around in solution that you had before. Okay. All right. I'm gonna go ahead and scroll a little bit. Give me just a little more room for D. Okay. All right. So chromium 3 nitrate and potassium phosphate. Possible products are, remember, no change in charge. So chromium 3, phosphate. And most phosphates are not soluble. Chromium is certainly not a group 1. So that is my solid. That's my precipitate. Plus potassium nitrate. That's a group 1 and a nitrate. So that is definitely still soluble. So that one is aqueous. All right. So translating, chromium with a +3 Nitrate has a -1, so I'm going to need 3 of those -1 nitrates to cancel out the chromium, and that's aqueous. Most nitrates are soluble. Potassium phosphate, potassium's +1. Phosphate is -3, so I need 3 of those +1s. Chromium 3 phosphate. Chromium is +3, phosphate is -3, so 1 of each. That's no mystery as to why that one's not. Trying to pull apart a +3 and a -3 would take a lot of energy. And the potassium nitrate, potassium is +1, nitrate is -1, and it is aqueous. Okay. Go back to charges when you're putting these products together because you are making something new. You're pulling these apart. They are apart, surrounded by water molecules. These subscripts do not carry over. But now I'm going to take care of the fact that we're not balanced. I have 3 potassiums, 3 nitrates. So if I put a 3 over here in front of potassium nitrate, that will balance my reaction. All right. Number 3 here, we don't have to write formulas. I know you're happy about that. And we are just going to see if the equations are correct. Have they written the products appropriately? Have they identified the precipitates appropriately? So I'm going to scroll. Okay. All right, so silver nitrate is definitely aqueous. However, sodium chloride is aqueous as well. Okay, so silver chloride is the other product, and it is the solid. All right, so actually, it's sodium nitrate, which is aqueous, and silver chloride, which is my solid. So that one was not correct. All right, here, cobalt goes with sulfate. That's been done correctly. And cobalt is +2 and sulfate's -2, so that looks good, and that is a solid. Or is it? Let me check the solubility rules. Most sulfates are soluble. There are some exceptions. It says sulfate up here at the top. In your textbook, and you will have received a copy of that figure. The top part, and it says it on here, is the things that are mostly soluble, and then the bottom is the things that are mostly insoluble. So cobalt sulfate, according to the solubility rules, it is soluble. So this is an AQ, and it looks like we have no reaction here because this is aqueous and potassium nitrate is aqueous, so this one is no reaction. Okay, number B. All right, C, copper should be with sulfide. It is, and it is correctly identified as a solid. Most sulfides are not soluble. And then ammonium with nitrate, and that is correct, it's aqueous. All right, last one, mercury should be with chlorine, and it is indeed a solid. It's an exception to the chloride solubility. Lithium and nitrate should be together, and it is aqueous. So your book, let's see, we had 2 incorrect and 2 correct, essentially. It goes against their 3 and 1 deal. Okay, now we've learned we're beginning to learn how to write the products using our solubility rules. The next thing we're going to do, and this is going to reinforce your charges and so on, is we are going to hone in on what is actually causing the precipitate in the case of this type of reaction that we're talking about today by doing what is called a net ionic equation. So this is a whole lot more detail, but this is going to give you the practice you need with the language. So it's not something that we're just torturing you with just because. All right, so we can write precipitation reactions and predict the products. So we want to know exactly which species are doing the reacting. Many of the ions, as you've seen, all those aqueous things, are just hanging out, or we call them spectators. So we are going to make sure that we understand that molecular compounds, that means covalently bonded, like water, stay together, and we will not break them apart when we write a net ionic equation. So we're going to take what we've just done up here, we're going to break it apart first into a complete ionic equation, and then we're going to cancel out the spectators, and we are going to then arrive at a net ionic equation which shows only the species that are reacting. So here are some rules of thumb. Do not break apart polyatomic ions, so you really do need to know them. Do not break apart molecular substances that are covalently bonded unless they are strong acids or bases, so you need to know those too. And we'll be coming again back to these again in exam 4 material. And of course, do not break apart solids because they stay together, and that's why they're a solid. There aren't that many strong acids and strong bases. What makes these different from other acids and bases is that they completely, in the case of the acids, they ionize. And I use that word because if you look at the elements that make up these acids, it's almost all nonmetal, nonmetal. Okay? And therefore there aren't any quote-unquote ions. But because of that that hydrogen, which makes it an acid, is so small, and the polar water molecule, that these come apart. The hydrogens come off, and I've got down here later in the notes, I've shown you how to do that. Strong bases dissociate. These are ionic compounds anyway. If you look at these, you've got a metal and a nonmetal. So all you're doing is you're just breaking apart what is a ionic compound. If you look and see which types are strong, it is your group 1s, okay, and a few of your group and some of your group 2s. All right, so we are going to break those apart in water when we start doing our complete ionic equations and then our net ionic equations. So I've got some examples in the notes of how to do that, and here they are. So if you are, these strong acids, you would rewrite them like this. Now here with sulfuric acid, we are seeing our first example of taking a subscript and bringing it in front. So when I break sulfuric acid apart, which has the formula H2SO4, and I know you're having a tough time seeing that, so let me make this a little bit bigger, okay? All right, there. This is the hardest thing for students with this ionic equation business. You take something that has a subscript, like this H2, and you take that subscript and you put it in front. The reason why is because this doesn't exist. It's two H pluses. So you're really writing it, when you write the ionic equation, you are really writing it as it exists. Okay? And because you know that hydrogen is just H plus, and if I have something like sodium sulfate, which is soluble, when I break that apart, it is not going to be Na2 with a 2 plus charge, okay, plus a sulfate ion. It is going to be 2 Na pluses, because that's what's really there, plus a sulfate ion. So remember, we're not breaking apart our polyatomic ions. We are adding our charges, and this is important practice for you. The bases are pretty easy. Remember that a hydroxide is a polyatomic ion, so we're going to leave it together. So if you encounter a strong acid or a strong base, and we will definitely in the next lecture, because we're going to do the same thing we're doing today with acid-base reactions, so we will see those in the next lecture. This is how you need to think about rewriting them. You're going to write them in ionic form. Okay, so I've got an example that we're going to work through here in the notes. We are going to take copper 2 chloride and sodium hydroxide, so there's a base for you, and we're going to determine that a precipitate actually forms. So our two possible new products are copper is going to now hang out with hydroxide as a possible new combination, positive with a negative, and sodium is going to be with chlorine as a possible new product. Well, if you look at your solubility rules, copper 2, oh, it is the copper hydroxide that is our solid, because the hydroxides are not soluble except for some exceptions. Copper is not one of them. Sodium, group 1, is certainly still soluble with chlorine. So when I write my complete equation, my formula equation, copper 2 chloride, aqueous, plus 2 sodium hydroxide, now this is balanced, aqueous. This is my product. So when I was thinking of putting my new things together, I said, okay, copper was plus 2, so it's still plus 2. Hydroxide is negative 1. So I need 2 of those negative 1s to cancel out the plus 2, and this is my solid. Sodium was plus 1, and chlorine was minus 1, so that's why the formula is this. The 2's in front are to balance the equation, and that's important because now we're going to take all of the aqueous things and we're going to break them apart into their ions, and that's done right here. Very tedious when you are typing it out because all those supers and subs. All right, so I'm gonna make that just even bigger so you can see it. There we go. In Word, the superscripts come out so small. So copper has a plus 2 charge. That's what that Roman numeral was for. Chlorine has a negative 1 charge. So again, I am taking a subscript and I'm bringing in front, because chlorine is Cl, chloride rather is Cl. It is not copper bonded to chlorine the element. It is copper bonded to chloride the ion. And chloride the ion is just Cl minus, so that's why I'm bringing that 2 in front. Now in this one, the 2 distributes to everything, just as if you were writing 2 times xy would be 2x and 2y. It's another way of writing the same thing, right? Well, that's essentially what you're doing here. So 2 sodiums and 2 hydroxides. Know your polyatomic ions. Solid, you're going to love the solids because you don't have to break them apart. And then your 2 sodiums and your 2 chlorines from the sodium chloride. And then here I reiterate about bringing the subscript in front. Okay, the charge is very, very important. You are reinforcing what you need to know about these species. The sodium ion is Na+, chloride ion is Cl-, hydroxide ion has a negative 1 charge. So this is the kind of practice that you really do need at this point because you're still refining your language. Okay, I'm going to scroll. Now, this is the complete ionic equation. Okay, and so what I do to go from this to this right here, which is the net ionic equation, is I cancel out spectators. Things that are exactly the same on both sides. So that would be sodium. It's exactly the same. That would be chlorine. Okay? Exactly the same. So the only thing that's causing the precipitate is copper and hydroxide to form this solid. This is my net ionic equation. Species that are high on the solubility chart are often spectators as they readily do not form solids. So most times sodiums and chlorines and so on and so forth. Now, be sure to practice these problems, including those in section 7 of chapter 7 involving stoichiometry of these reactions. All right. I'm going to have double check to make sure that's chapter 7. In fact, I'm going to pause here and go get the... Okay, I was correct. It is chapter 7. Don't worry about this word at this point. Most of you don't even know what it means. We're going to get to it in this set of material for exam 3, but don't worry about that. Okay, so we've worked through one example, and now, guess what? You get to work through some more. All right, and what I'm going to do first with you is we're going to go to this link, and it has a nice little practice. It has pictures. I think it's a good point to start at this point because it lets me go there. All right, I know it's already pulled up on my browser. Let's get out of Facebook. Okay, so this is a link. You can certainly follow it and go through it yourself many times if you'd like. So it's kind of going back and reiterating what we've done in this lecture, which is also always helpful. So when two solutions, and right here, there's the solution, there's another one, homogeneous mixture, containing ionic compounds are mixed together, one of two things can happen. Nothing, if all the combinations are soluble in water, so you still have those same 4 ions. Okay, so same 4 ions still floating around. All right, so nobody formed a precipitate. Okay, or one, and you could have more combinations. It's possible to have 2 precipitates. So we're going to play these movies and look at the animation. It might help some of you to understand what we're talking about, and then we're going to go through some examples here at this website, and then we'll go back to the notes and finish it off with a few more examples. So I'm going to play this movie. So here's our copper chloride, and looks to me like we're adding some sodium carbonate. So the sodium carbonate is the clear one here, very soluble. The cobalt chloride was soluble, but now you see something happening down here at the bottom of the beaker. And so the animation, so the the possible combinations are sodium goes with chloride, which is still soluble, and I wish they'd had some of those kind of floating around up here, some sodium and chlorines floating around up here. So I'll write them in. They're still there, okay, floating around. But when those cobalts and carbonates come together, +2 -2, it's not soluble. Carbonates are for the most part are not soluble, and so that's your precipitate. So I'm going to play this one more time. So there's your couple, okay, down here at the bottom that just love each other so much. All right, so we're going to go to the next piece of this. So they're showing you here about putting the products in place. So here are the 4 ions that you had, your sodium, your cobalt, your chlorine, and your carbonate. It is the carbonate ion that is not soluble with most ions, with these exceptions, same thing that's in your solubility rules. All right, and that is your solid. So the positive going with the negative. This positive is going to go with this negative. But we're going to go back to charges, and we're going to write NaCl because +1 -1. Chloride is soluble with most ions, but not with silver, mercury, or lead. So sodium is very soluble with most things. All right, so now let's do another one. So we're not doing net ionic equations here, but we will when we go back to the notes. In fact, we'll do this one. So you're going to give this a try. So pause at this point and combine lead nitrate with sodium iodide. Write your 2 products. Determine which one is your soluble product and which one is your solid. And then come back. So it's asking us here in this little thing, which anion should you put with the lead on the product side? So is lead going to go with nitrate on the product side? No, because it's with nitrate on the reactant side. It certainly won't go with the sodium because they're both positive, so it's going to go with the iodine. Okay, and lead is +2 over here, so it will be -2 I'm sorry, plus 2 over here. And then it even guides you through what's your possible product formula. Is it PBI, PBI2, and so on? Remember, no change in charge, so if it was lead 2, it's still lead 2. Iodine has what charge? -1. So this is my correct formula for lead 2 iodide. Is it soluble? Hint, use the solubility chart. No, it is insoluble. And which anion should you put with the sodium? Well, no, not iodide, because sodium's with iodide over here. Should you put it with lead? No, they're both positive, so nitrate is your correct anion or negative partner. And the correct formula for sodium nitrate, sodium is +1, nitrate's -1, so it's this first one. And is it soluble? Yes, it is. Okay, so what I'd like to do is stop here and go ahead and write the ionic equation. So if you want to pause and give that a try, I'm going to do it right here, and then I'll return to the notes and do a couple more examples. All right, so lead is +2. When I rewrite this aqueous reactant, the 2 here is going to come in front of the nitrate. I have 2 nitrates. Of course, they're both aqueous, but I'm not going to write that in because I'm lazy. Now I do need to balance, so let me do that because that needs to come, into play. I need 2 sodium iodides and 2 sodium nitrates to balance this reaction. So now that 2 is going to distribute through both of my ions because it's in front. Okay. Solid, leave it alone. And then the 2 here distributes. So 2 Na plus 2 nitrates. Okay. And that's my complete ionic equation right here, complete ionic. Now to get my net ionic, I cancel out the spectators. Nitrate is a spectator, and sodium is a spectator, both high on the solubility chart, so that's why. So the 2 things that are forming the precipitate are the lead and the iodine, and of course they're aqueous over here. And I form the solid lead iodide. So here's my net ionic equation. Okay, this link is in the notes, so you can give it a try. I'm going to go ahead and go back to, oops, let me get my pointer back. Go back to the notes. Okay, number 2. Mercury ions can be removed from solution by precipitation with sulfate ions. So we are going to take a solution of lead 2 nitrate. Let me give myself some room here. Mercury 2 nitrate, and we are going to react that with potassium sulfate, and it's telling us what we're forming. So I am going to write my formula equation first, since I've been given all of my reactants and products here in the question. So I've got mercury 2 nitrate, so that means that mercury is +2, and nitrate is -1. So I need 2 of those -1s to cancel out the +2, and that's aqueous, plus potassium nitrate. Potassium is +1, sulfate, and sulfate is -2, so I need 2 of those potassiums, and that's aqueous. See, it kind of tells you that in the directions. To make solid mercury 2 sulfate, so 1 of each is good, and aqueous potassium nitrate. Back to charges, potassium is +1, nitrate is -1, so 1 of each is good, and that is aqueous. All right. To balance, I'm going to need to put a 2 here, and that should take care of it. All right, writing my complete ionic equation. I've got Hg with a +2. I've got 2 nitrates. I've got 2 potassiums and a sulfate. That 2 only went with the potassium. Put in your charges. Leave the solid alone. And then your other product, the 2 distributes. All right, so my spectators are again nitrate and potassium this time. So my net ionic equation, I'm going to write it up top of number 2, is mercury with a +2, aqueous, reacts with sulfate, which is also aqueous, to produce the solid. And that is my net ionic equation. Okay. Going to scroll so we can do this last one together. All right, so I'm going to give myself some more room. All right, if you'd like, go ahead and pause the video and give these a try. But the first thing I'm going to do is determine whether or not I have I think all of them have products, but that's the first thing I'm going to do. And then I'm going to start writing formula equations and complete ionic and net ionic equations. Okay. So potassium acetate is a possible product. I'm trying to write small so I don't use up too much room. And potassium compounds are soluble as well as acetate ones, so this is aqueous. And lead chloride is going to be my solid. Okay. Kind of went off in the black there. I'll get that back, don't worry. I'm going to give myself even more room. There we go. Okay. I'm going to do all that for these 3 that I can see right here. So lithium chloride, lithium compounds are pretty much soluble because that's a group 1, so that's aqueous. Plus strontium sulfate, we've come across that one already today. So strontium sulfate is my solid. Double checking the solubility rules on that. Yes, it is insoluble, top of your solubility rules on the right. Next one, potassium sulfide. Potassium compounds would be soluble. And it looks like we have a no reaction here. So because this is aqueous and the calcium bromide is also aqueous. So we've got a no reaction for C. No reaction. Okay, so let's do these A and B. First of all, writing our complete ionic, well, our formula equation. So KCl, aqueous, plus Pb with a +2, that's what the Roman numeral's for, acetate, and it has a -1, so I need 2 of those, and that's aqueous. Potassium acetate, K is +1, acetate is -1, so 1 of each, aqueous, plus Pb with a +2, and chlorine with a -1, and that's an exception, so it is to the solubility of chlorides. So there is my formula equation. Now I'm going to balance. I need 2 potassium chlorides, and I need 2 potassium acetates. Okay, complete ionic equation, 2K plus, distributing that 2, Pb +2. The 2 is for the acetate, so it comes in front. I guess another way to look at bringing these subscripts in front is if it doesn't go with the formula, then you know to bring it in front. It's one way to look at it. Certainly if you have a parentheses with a number on the outside, you're always going to bring that in front. And then leave your solid alone. You'll get to where you really like the solids because you don't have to do anything with them. And now what are our spectators? Potassium is a spectator and acetate is a spectator. Oop, forgot my 2 here. All right, so that cancels out as well. So my net ionic equation, and I'll go ahead and put my AQs in here, not as tedious, plus 2Cl minus makes my lead chloride solid. Okay. B, lithium sulfate. Lithium has a +1, sulfate has a -2, so I need 2 of those lithiums, and that's aqueous. Plus strontium chloride. Strontium is +2, chlorine is -1, so I need 2 of those, and that's aqueous. Lithium chloride. Lithium's +1, chlorine's -1, aqueous. Worry about the balancing when you're done. Strontium sulfate, strontium's +2, sulfate is -2, so 1 of each, another +2, -2, and it is a solid. Splitting up my aqueous things, the 2 comes in front for the lithium. Oops, my bad. Lithium, not potassium. 2 lithium with a +1 charge, aqueous. Put in the charges, it's so important. It gives you the practice you need for what these species really are and reinforces charges. I'm not going to put aqueous on everything over here. Okay. Balancing, sorry. So I get over here and I realize I haven't balanced. 2 lithium chlorides, I believe, will do it. Okay, so 2 Li plus 2 Cl minus, and then leave your solid alone. And then cancel out your spectators, and that would be your chlorines and your lithiums. And then it's just sulfate plus your strontium makes your solid. All right, moving on to D, and that will finish us up for today. Scrolling. All right, remember C had no reaction. So chromium, whoa, look at that, my bad. Or nitrate twice, oops. Should have not done that. This is the one I don't want because the 3 goes with the chromium. All right, chromium 3 nitrate and potassium phosphate. Possible products are chromium 3 phosphate, which we've already done one of those at some point today, and that's my solid, as most phosphates are not soluble, and potassium nitrate, which is still aqueous. All right, so translating into formulas, chromium with a +3 and nitrate with a -1. So I need 3 of those -1s to cancel out the +3. Potassium and phosphate, +1, phosphate, -3. So I need 3 of those +1s, that's aqueous. All right, then chromium 3 phosphate. Chromium is +3, phosphate is -3, so 1 of each. No, we've done this one already. Solid, plus your potassium nitrate. Potassium is +1, nitrate is -1. So I always tell students, write these formulas for these chemical reactions with blinders on. So while you're writing the formula for potassium nitrate, don't look over here because it had to the reactant side, to the left, because it has nothing, with the numbers over here, has nothing to do with the numbers that you're going to be putting into formulas over here. So you're going to write potassium nitrate as if you were doing it in isolation. Now you can look to both sides for balancing. I see 3 nitrates and 3 potassium, so I need 3 potassium nitrates. And I've got 1 phosphate, 1 phosphate, 1 chromium, so we're good. All right, complete ionic equation. Chromium with a +3, plus 3 nitrates, parentheses with a subscript on the outside tells me bring it in front. 3 goes with the potassium, bring it in front. Only 1 phosphate. And then chromium phosphate solid, leave it alone. And then the 3 distributes 3 potassium ions and 3 nitrate ions. My spectators are nitrate and potassium. And so my net ionic equation is chromium plus phosphate, and that's aqueous, makes chromium phosphate solid. Now before we leave today, I want to caution you about you smarties who are going to see that you make a solid and then skip this complete ionic step. I'm going to show you one example where everything doesn't cancel out like it has for us so far today. So let me write an equation real quick, and I'm going to do it from the formulas. I'll just do it right here. So I'm going to draw a line here. So if I take calcium carbonate, which is not very soluble, you check your solubility rules for carbonates. That's down at the bottom. It is not a soluble compound. That is a solid. Plus, we haven't done one with an acid, so let's do one with an acid. Let's do, let me go ahead and do hydrochloric acid. Okay, and that's aqueous. All right, possible products are calcium with chlorine. And if you check your solubility rules, that is aqueous. The other product, and I'm glad I picked this one, is hydrogen with carbonate. Hydrogen carbonate does not really exist. As soon as you produce hydrogen carbonate, it falls apart into water and carbon dioxide. Those are 2 molecular compounds that you cannot break apart. So this is all nonmetals. All right, so we haven't done one with an acid today, so we'll be breaking that up. It's a strong acid, so I need to scroll, and I'll see if I can get it back. Okay, need a little bit more room. No, not gonna let me. Let me just erase some, and then I can just use the area above, if you don't mind. Okay, so I'm going to erase this stuff here. Okay, so let's write our ionic equation, complete ionic equation. I cannot break up that solid, so it's CaCO3 solid. I can break up the acid, balance, 2 here, 2 chlorines. Okay, that's good. So I'll break up my acid. Okay, to make Ca with a +2 plus 2 chlorine ions plus H2O plus CO2. And those are molecular compounds, so we are going to leave them alone. This is a liquid, this is a gas. So the only thing that cancels out is chlorine. So my net ionic equation is calcium carbonate plus this acid makes, this is like chalk and an acid, makes water. And I left out the calcium, I'll put it back. And CO2. And calcium still dissolved in solution. So be careful. Not every single example, you're going to cancel out everything except for the 2 species that made the solid. And that brings us to the end of lecture 12.